Okay, what we're looking at today is a Philips PM6673 universal frequency counter. This frequency counter is rated from about 5 Hertz to 120 megahertz, but it has several really unique features, probably the most significant of which is that it's microprocessor based, and that it gives you maximum resolution because of that, especially at the lower frequencies, but at any frequency it maximizes it. Give an example. On a traditional digital frequency counter, if you tried to read something, say in a 10,000 Hertz range, and yet you've got a capability of 9 digits, well, the most it's going to show you is the 5 digits of the 10,000. It's not going to show you the other 4. And reason for that is it counts down to the whole count, and that's that. Now you could go to period and measure the period of the cycle, especially at the extremely slow frequencies, and it would count up some very small bit of timing pulse. And let's say the timing pulse was a 1 megahertz pulse, and let's say that it counted up 1,000,000 of those. Then it says, well, in 1 second I counted 1,000,000 of these pulses, so therefore I must be at 1 megahertz. Probably the key feature about this counter is that it uses a microcomputer to actually calculate and display the resulting frequency. On a traditional counter, you would have a gate where one input of the gate would be the frequency coming in, and the other input of the gate would go to a timer, and for some fraction of a second, or maybe for a full second, depends on the unit, you would allow the gate to allow the incoming pulses come in, and you would count those pulses in the counting circuitry. And at some point in time, your timing pulse quits, and that shuts off the gate, closes it, doesn't allow any more pulses to come in. And then you go through the display cycle, and you display the number of pulses you counted. And it works well. A lot of, I'd say the majority of counters were based on that idea. But as your frequency goes lower, so does your resolution. If I have a counter that's capable of reading 9 places, but my smallest or least significant digit is a whole hertz, then 9 places, then I'm talking 900 million hertzes, or 999,999, blah, so on. It'd be my maximum display. But if I can only display a full hertz, anything coming in lower than that, let's say a megahertz, I can only display on the first 6 places. So 3 of the places are lost. If I'm displaying 10 Hertz, then I only have the first 2 places. 1 Hertz, I got the first place. So I lose the resolution as the point, as the frequency would go down. On this particular counter, we're not looking at counting the incoming pulses from the frequency being measured. Instead, we're doing something more like a period measurement. We've got a series of very fast known pulses coming in on the timing gate, 100 nanoseconds I think in this case. So, and we're allowing the incoming frequency to control the gate, and we're counting the number of high 109 nanosecond pulses that we can get through. And if we know that, we counted up the number of 100 nanosecond pulses, and we know they're 100 nanoseconds in duration, then we can figure out the fraction of a second that was involved in that one cycle of incoming frequency. And if we know that fraction of a second, and we do the inverse of it, then we know the frequency itself. And then if we have a system that can take that frequency and display the resulting number in 9 digits, and put the decimal point in exactly the right spot, then you have a very high resolution frequency counter that gives you the fractions involved in that 9 digits as well. So maybe I would read 1,000,000.007 instead of just 1 million. Or if I'm reading 10 hertz, instead maybe I get 10 point, and then I get 7 decimal places. I mean, it's that kind of work that's going on in here. It's all handled by a microcomputer that's inside of this unit, and it works very well. We're going to go ahead and check the calibration of it against a Rubidium Standard. I have a Rubidium Standard here. Inside this unit is an L Pro Rubidium unit, and then we have, along with it, some associated electronics to allow us to divide the signal and provide the power supply and so on. It provides a very, very accurate 10 megahertz signal. We're going to see where we sit on this counter relative to that 10 megahertz signal. So let's do that now. Okay, we're connected up. We see 10 megahertz on the screen right now, 10.00000 megahertz. And let's go ahead and turn the resolution up. I'm going to do that by turning up my measuring time here on the front panel. In fact, I'm going to set it for 1 second. Alright. We're going to give this unit a chance to count a couple of times. It has. And we see that we are counting 9,999,997 or 8 cycles coming in on the input line, the frequency line. So that would mean that I am somewhere between 2 and 3 cycles off of 10 million exactly on this unit. You could do a little math. Go for the 3 if you want. Take the 3 cycles, divide by 10 million, and that's your error. It's very small. Okay, let's turn up our resolution again. Now we're going to count every 10 seconds. So in 10 seconds, basically it's going to count how many 100 nanosecond pulses make it through the gate as controlled by the incoming frequency, and then it's going to do the math and present the results on the display. Let's let it finish this next cycle, and then we'll tell you that. Alright, we just did. So there's 9,999,997.2 cycles that this thing counted. That's the calculation of the incoming frequency based on the number of 100 nanosecond pulses we counted. So we are less than 2.8 cycles off in 10 million. Very accurate. I have a laboratory grade Fluke 1953 right underneath it here, and it also is connected up. Go ahead and give you a look at it if we can. I'm not certain how well it shows up on this camera at this angle, but we are reading 9,999,997.0. It goes 0 to 1, so yeah, there's a 1. So we are reading within 1/10 of a hertz of each other on both units. In fact, right now both units are reading exactly the same. So in accuracy, I think we're right. We're good. Let's go ahead and check the frequency capability of the unit, and we're going to do that utilizing a PTS 500 for our high RF frequencies, and then we'll use a Hewlett-Packard 3320 frequency synthesizer for the low frequencies. And I'm just going to do probably 10 checks. We're not going to take this in and make it too laborious, but let's go ahead and connect up. Alright, we're connected. And I'm going to turn my time down. Right now we're reading a 100 megahertz signal from my PTS 500. This thing is rated, this Philips is rated at 120 megahertz, so we should be able to go up to 120 without a problem. Alright, there's our 120 megahertz. But will it do 150? Yes. Will it do 170? Yes. 180? Yes. About 190? No. Alright, so we were able to read up to 180 megahertz with this unit. That's pretty spectacular, because that's let's see, 180, that'd be 60 over 120. That's 50% additional bandwidth that we didn't know we had, according to the specifications. Now, it's something that I wouldn't want to practice too often, because as you get, the higher in frequency you go, the more sensitive you are to the voltage coming in. The power becomes a problem on the input circuit. So I would cautiously utilize that capability, but it's capable of reading the 180 megahertz. I just proved it. All right, now let's go the other direction. Let us go 90 megahertz, 50 megahertz, 10 megahertz, 9 megahertz, 5 megahertz, 1 megahertz, 900 kilohertz, 500 kilohertz. Now, I'm actually already below my my usable range for this PTS, so we're going to switch over at this point to my Hewlett-Packard. All right, and here we are again at 500 kilohertz, 200 kilohertz, 90 kilohertz, 50 kilohertz. $10 kilohertz. Now we can turn up our resolution, but it means we're going to incur a little bit greater count cycle. But just to show you that we can do it. There we go. So there's 10 kilohertz, and it's reading 9,999.9973 hertz. Alright, let's go ahead and crank her down again. 9 kilohertz. And let's shorten up our gate. It's taking too long. All right, let's go to 5 kilohertz. And how about 1? So there's 1,000 hertz. All right, then we're going to change our There's 900 hertz, 500 hertz. Now if this had been a normal counter, that's what you would have seen. But with this counter, you get to see that. And if we want, we can turn the resolution up more until we get 9 digits. That's the beauty of this counter. Alright, let's take it down to 100 hertz. And $90 hertz, 50, 10, 'Alright, here we go. 9 hertz, 5 hertz, 3 hertz. Now we've actually gone but lower than the rating on the counter, so if we can hit 3, we're doing very well. Yep, 3. Let's try 1. Nope, we can't do 1. We did 3, that's pretty good. Here's 2. There's 2. So it actually read down to 2. Amazing. Okay, so we've gone from 2 hertz to 180 megahertz on a counter that's meant to go from 10 to 120. So it's capable. We also tested its accuracy. It's accurate. We saw some of the features. Let's look at a few more. Go ahead and disconnect our. Well, no. Let's count incoming cycles. Let's go ahead and do that. Let's go up to 10 cycles. Alright, we're at 10 cycles, frequency coming in, or 10 hertz. And then let's put ourselves in the count mode. And we're counting the incoming pulses, so totalizing them. We could stop it at any point. And if we were looking for pulses, for instance, on a line where we didn't want them, you know, we just suspected that there was some kind of a pulse coming down a line that should be otherwise clean, we could utilize this this count to indicate the number of those pulses that made it through to the unit of that size. We have some different filters here that change the way that the unit reacts to the incoming pulses, requiring additional pulse width or a duty cycle. We also have a period measurement that we can make. All right, like right now, it's telling me that, so we're displaying 100 milliseconds. If this had been 1 millisecond we displayed, that'd be 1000 hertz. If it had been 10 milliseconds displayed, then we'd be at 100 hertz. But since we have 100 milliseconds displayed, we are at 10 hertz. And we are at 10 hertz, so it's reading the period accurately. And then we can display the frequency accurately. We can hold the display at any time by hitting the display hold button. It won't cycle anymore. We can release it, we can reset the count. We can check the frequency internally just to see if we're accurate. So we're reading 10 megahertz. And we can adjust our sensitivity. We have two levels of sensitivity. The first level goes 0 to 10 millivolts, and you can pull out that button and you can go up to 200 millivolts. So along with the counter, I'll throw in a set of test leads. These are coaxial gator clipped ended test leads. And the manual is here. It gives you theory of operation, information about calibration and troubleshooting and operation, adjustments. Here's your schematics. So we've got a full package here. It's a very beautiful unit, very high resolution. It's in good shape, very good shape. Case-wise, you know, it's got some use on it. It's got some scratches. We'll give you a good look at that. But all in all, it's in good shape. It works great. Just giving a little look at the interior of the unit. Nice workmanship. Has a quality look to it. Clean. No fires are obvious in here. So there you have that. Here we have a look at the underside of the chassis. Again, clean, nice workmanship, no damage evident. Here we're getting a look at the back of the unit, and one option and feature that I forgot to mention is that this contains the PM6673 IEEE 488 interface. So for you people out there that are into connecting your instrumentation up to computers and collecting the data and so on, the interface is here. I don't have the expertise to utilize it, so I haven't tested it, but everything else about the unit is working fine, so I would suspect this would too. It does have an internal-external frequency standard switch and an input. Here's your internal standard out, so you could use the 10 megahertz, or you could measure the 10 megahertz to see how accurate it is, use it for something else, or you could feed a different 10 megahertz signal in that gave you additional capability. And then there's some resets and so on, I think, that possibly are somewhat related to the IEEE interface. Works on a 115 or 220 switch selectable, and the well, I think the serial number on this, it says NC, so I'm thinking that's the serial number, is 944606673O16. Made in Sweden by Philips. Alright, so thank you. So thank you for listening.